Okay, cool. Get started. Is lab 4 going okay? A lot of people were making good progress in the lab yesterday. Please start it as soon as possible. Some people were running into issues with Bluetooth connection, so hopefully you were able to resolve that. Worst case, I may recommend just to kind of move on and get the learning outcomes from the assignment, but not spending too much time. Might recommend if you need to use someone else's computer to do the connection, or if you need to use the Raspberry Pi or use your computer at home, something. Some people are just having troubles with Bluetooth. So if you're getting weird connection problems, I don't know of a solution for anything at the moment. So good luck with that. Feel free to keep messaging on Piazza and offering potential solutions and things to your fellow peers and students. But start early because you may run into issues. It may also just work first try for you. So it's kind of variable. Okay, the first part of the lab though requires you to get the accelerometer and gyroscope working. Okay, in what applications would we want to use a gyroscope or accelerometer beyond just this lab where the idea is you tilt your board and then you can control a mouse, which is kind of a dummy project. But why are accelerometers and gyroscopes so important? Yeah.
I mean, I guess there's a lot of other things that use them, I don't know, vehicles maybe.
Sure. Vehicles, absolutely, especially if they're in the air. If you are controlling a helicopter or something, and you need to figure out at what the how to control the helicopter blades and then the rudder blades. If you have a quadcopter or some sort of drone. If you are working for some defense company, probably gyroscopes and accelerometers can become your best friend. Anything else? Maybe if you're up in space or something, maybe you're exploring Pluto and you somehow need to figure out, it's okay, how do I tilt my rocket engine to now point in this direction to slow down or speed up according to whatever rocket mechanics I need. Accelerometers, gyroscopes, extremely valuable. But what do each of them do? What does a gyroscope do? I don't know. What is the data that we can get out of the gyroscope when we read it? Yeah.
Well, I know it's can come from any direction, so XYZ coordinates.
Sure. Yep. So it's three-dimensional XYZ, right? What happens when we read out a value at in a gyroscope? I don't know. Well, so actually, I have my iPad right here, and I downloaded this cool app called Sensor Toolbox or something. And what's cool is actually all Apple products and most phones will have built-in accelerometer and gyroscopes inside of them. And so here we can see the accelerometer data. Okay. Just wondering, does anything on this look familiar? Anything standing out? Yeah, look at this. So we can see right here that we have this 9.7 meters per second value right there. And this looks very much like gravity, right? So the idea with at least the accelerometer is that there is some sort of internal kind of stress tester. It's checking where it's testing kind of the orientation of your device, and then it's comparing the readings of kind of whatever internal tensile strength kind of monitors you have, and that converts it into how much strength is needed to lift up that sensor in order to oppose gravity. So here you can see that in the X direction, it looks like it's needing to kind of pull up on that sensor at 9.7 meters per second. So therefore, it knows that our device right now has force applied on it of 9.7 meters per second. If I now were to maybe pick up this iPad, then you could see that just for a second, it seemed to have it went up and then down and whatnot. So if I were to hold the laptop, if I were to pick up the iPad, move it up at maybe a constant acceleration of maybe 10 meters per second up, then what would we imagine now this value would say if I moved it up at 10 meters per second? What should this now say? Probably 19, right? Yeah, if I now shove it down at 10 meters per second, now I should say like close to 0. Yeah, that is how this works. Then also, like, watch what happens if I tilt it. So if I tilt it, now it looks like that 9.7 meters per second has now gone down to now like 8.6, which is odd, right? Like, does that mean that now there's less gravity acting on that? Or like what happened? Yeah, what's going on? Yeah.
I think might be because I guess the force of gravity is being like distributed across like the different sides.
That's exactly right. Yeah. So instead of having just like a single sensor now reading out just like the x value and like all of the gravity is being like read in through that value, now when you tilt it, now the like it looks like the that's funny. It looks like there's 3 x's here. That's funny. I think it's supposed to say like x, y, z. So it looks like now the y and the z like vectors are now splitting this gravity force vector amongst the two of them. And if I were to tilt it all the way, we would see that it would actually like fall to 0, and then the y vector would go all the way up to 9.7. Yeah, absolutely. Okay. Now here is the gyroscope data. Okay. Looks to be like it's just about 0 right now in steady state. But if I now like kind of wiggle it a little bit, then we should see that now we start to get like larger values. And what kind of digit here, or which place seems to be affected the most when I wiggle it in this direction?
The x.
Yeah, it looks like it's x. Okay, what if I now wiggle it like in this direction?
Y.
Yeah, y, okay. And then z, I'm guessing, would be like if I twist it. Yeah, you can kind of see like, yeah, there we go. So gyroscope, what would we imagine now the gyroscope does? Yeah?
Like measures rotation.
Exactly, yeah. So the gyroscope is basically just measuring the rotation. Yeah. And notice that the accelerometer up here, the accelerometer like seems to always kind of tell us our position, but the gyroscope tells us instead our speed. So if I wanted to now potentially get position from gyroscope data, what would I need to do like with this data? Yeah.
You would have to convert the angular speed, I think, to linear speed.
Potentially. That's not quite what I'm looking for. How could I find the like orientation of my iPad? Because remember, like if I like just kind of pick it up and just hold it here, it's gonna still like stay 0. But when I set it down, it like spikes up for a second. So it's only outputting like a large value as I'm moving it. So how do I now get the actual like data from this gyroscope? Yeah.
Just time yourself, like the turn and just multiply, or multiply radians per second to just get radians.
Multiply radians per second. Potentially. What's the calculus term that I'm looking for here? Yeah.
You have to integrate?
You have to integrate, right? Yeah. So we integrate with respect to time, and then that will now give us just radians, which is kind of the same thing as if you wanted to do like a trapezoidal like multiplication thing. But yeah, anyway, so cool. Gyroscope data. The way that we use this is we integrate it over time, and then that will give us now the position. Because this is just showing us like our speed at any point, like our rotational angular velocity. And only when we integrate that will now give us our actual like angle as opposed to just velocity. Yeah. Okay, cool. So one of these seems like a little bit easier to use, right? It's like the accelerometer, right? It's like pretty clear. It's like, okay, yeah, like this just immediately gives us the position of the iPad, and we don't have to do like any integration on it or something. Okay. When would this accelerometer potentially fail? Like here, like we can very clearly see it's like, okay, yeah, so it's the iPad is like facing up right now, like we can clearly tell the position, and and I bet like if I were to like rotate this or something, then it's like very clear like what the position of the iPad is. But in what case will the accelerometer not work for us? something. Okay, wait, ponder that for a second. I'm going to show you these examples right here. Okay. So picture that, this is Earth, right? Imagine we have this sensor right here that is maybe staying still, meaning it's not moving up. Maybe we can imagine sitting on like a platform or something on Earth. As opposed to this one, maybe it's kind of backwards. I'm saying it's -10, so it's actually falling now at 10 meters per second, like towards the Earth. Okay. And then we have this sensor, which is moving up at 10 meters per second away from the Earth. And then we have this sensor right here, which is moving down at 20 meters per second. Okay, really quickly, I want you all to write down what you would imagine the Z acceleration value would be in the sensor for each one of these 4 values. Okay, I'll give you a quick hint. This is the current state right now because our iPad is not moving at all, so we should imagine that this is has an acceleration of 10 meters per second. Yeah. Okay. Okay, is this what we got? So here it starts out as 10 meters per second. Then here, if our sensor is falling, that now means that it's actually reading 0 acceleration, kind of definition of falling. Okay, and then in this example, we have that our sensor is moving up, so now it's fighting against gravity, and now our sensor is going to read out 20. And then in this case, it's now falling at 20 meters per second, which means that now we are actually pushing it down with a force that will give it now 10 extra meters per second. Okay, is this good? Okay, well, do we see an issue here? Look at these two values that we're reading right here. So this is 10, this is -10. It's very possible that I could have just flipped this all around. And if I had flipped this around, then now it would be completely indistinguishable from this case, where if we now are pushing it down, but now it's an upside down vector. So now it looks like we're pushing it, or now it looks like it's receiving a vector of 10 meters per second. Okay. Yeah, so what's the problem here? The issue is that we can't actually rely on the accelerometer all the time in order to figure out our rotational position, especially when the object itself is moving. When the object is staying perfectly still and we rotate it, it's very clear we can get the rotational data out, no problem. But the second that it starts moving, for example, if you are designing a helicopter or a drone or something, then now all of a sudden you would not really want to strongly rely on the accelerometer. Could still be useful data, but it probably is not going to be the most important bit of information that your sensors are feeding into. Yeah?
Well, so the thing is an acceleration, it is basically the rate of change, I think, that the velocity changes, but it's not, I think, the velocity itself.
Correct. Right, yeah. So this is just showing you the acceleration, but it's not showing you the velocity. Right. Yeah, absolutely. Cool, okay. So therefore, if we now wanted to design a Bluetooth mouse that now used the rotational angle of our ESP board, I guess now the question is, should we use the accelerometer or should we use the gyroscope? Yeah. Actually, I guess we could probably use either one. For the accelerometer, because we're probably going to be holding the mouse pretty still, we're not going to be moving it all around and messing up the data on it. Since it'll be still, we could probably just use the accelerometer. Or if we want, we could also just use the gyroscope. An issue with the gyroscope though is as we add up the like angles. Like as we tilt it down, maybe like we sum up all of like that rotational like velocity, and then when we tilt it back up, there may be drift. So even though we tilt it all the way back up, and all of a sudden it may not know that we are perfectly at 0. But maybe that's fine because we'll just be off by like a few percent or something. Maybe for a mouse, it's not as critical as maybe something that is like carrying passengers in the air. So okay, yeah, so we could probably use either one. Okay, and yeah, our ESP has the sensors on here for us. So this. Okay. Does anyone know which thing here is the sensor for the gyroscope and accelerometer? Yeah. Okay. Any guesses for what IMU stands for?
I remember the I stands for inertia.
Yeah. Wait, go and tell the person next to you if you know. What does IMU stand for? So IMU stands for inertial measurement unit. And the point is, yeah, it's supposed to measure your inertia, but using multiple sensors. As opposed to like, if it was just an accelerometer, it might just say like accelerometer. Or if it was just a gyroscope, it might just say gyroscope. But this is an inertial measurement unit, because they're trying to be fancy. Yeah, okay. And the ESP can communicate with this IMU over I²C. And I want to pull up the data sheet for it really quick. Okay, good. So here's the IMU listed on the documentation for the Rust board. And so now we can go and open up the data sheet for this, go and check it out. And, okay. So have many of you gone through this data sheet at all? Look through this? Yeah. It's kind of a beast. It's not quite as helpful as the temperature and humidity sensor data sheet. This one's a little bit kind of longer and a little bit more dense. And, we could go through all this, and we will go through a little bit of it. Probably the most important thing starting out is there's a way that we can bring it up out of sleep. And I'm trying to remember where it is. I think is this right? Power management. Yeah, that's right. It's kind of unwieldy, but you can kind of just, if you want, you can just kind of start at the beginning, and it'll walk you through everything. It takes like 20 minutes to read through the first introductory sort of like things. But okay, so here is the power management, register, and so we interface with this using I²C, and so here we can see that the address is 1F. And this is not the like I²C device address, but instead this is the address for like after we send a byte to the device. So when we send this 1F value to the device, then we can go and set the value of our power management like register. And we can see right here there are reserved bits for our power management register. If we scroll up, we can see, so there's bit 0, 1, 2, and 3. So it looks like the Excel mode takes up bit 0 and bit 1. So okay, it looks like there would probably be 4 separate modes for the accelerometer, depending on if we send like 0, 0, 0, 1, 1, 0, 1, 1. And then same thing with the gyro mode, because this will take up bits 3 and 2. So I'm guessing if we wanted to just initialize both of them at the same time, then we could just write to kind of this lower 4 bits right here of the power management register. Okay, and let me also, I think I can look up gyro mode. Yeah, so here's the gyro mode documentation. So it looks like in 0, 0, so this is the default case. So if we had written 0, 0 into this register, then this will turn the gyroscope off. So if we wanted to go into like standby, like maybe our drone that we are building ourselves, maybe after the drone lands, maybe we want to turn off all like the accelerometers and gyroscopes and things to save power. So if we want, we could write in 0, 0. Otherwise, we could probably just set, we could probably just turn on one of these. Maybe just a low noise mode. I think that makes the most sense. And then, yeah, it looks like the gyroscope needs to be kept on for a minimum of 45 milliseconds. So when transitioning from off to other modes, do not issue any register writes for 200 microseconds. So this is just extra things that you would need to make sure. So anytime you set this mode, you just don't want to set anything else for a second. Okay, here's the accelerometer mode. And similarly, so yeah, here's 0, 0, which turns the accelerometer off. It's like 0, 1 as well. But if we want to do, yeah, low noise mode, then we set 1, 1. Okay. And then after we wake up the sensors, then what we can do is read out the data. And the data we can get, and I kind of just have it memorized, but let's see if I can find it in the table of contents at least. Okay, there we go. So here, so we can see, yeah, so Excel data X1, Excel data X2. I'll go and click on one of these. So we can see that Excel data looks like it is like telling us that this Excel data should be 16 bits. And if we now read from this register, which has the address of 11 or B in hex, then this will give us the like top bits, the top 8 bits of this Excel data X value. And similarly, like if we wanted to read the bottom 8 bits, then we would read from like X0, this is at address 12. And then we could keep going. So this is how we read out the Y value. This is how we read out the lower bit or lower byte of the Y value, similar upper bit of the Z value, and lower bit of the Z value. And then here's now how we read out the gyroscope data. So we can see like all of the data that we want to read out of this, this sensor, it's all kind of localized in here. It's addresses 11 all the way until it's like, yeah, address 22. So everything from 11 to 22, that is like, yeah, the accelerometer, X, Y, and Z data, and the gyroscope, X, Y, and Z data. And if you want, you could now go and implement this now like in the same kind of way that we've been doing I2C stuff, where you go and manually read out everything and yeah, using like the I2C master transmit and whatnot. What is nice though is ESP actually does provide a nice like library that we can use instead that will simplify the like I2C transactions and whatnot. So I want to show you that. But yeah, before I go to that, are there any questions on this? Is this how other people have started this lab? You're looking at the data sheet and you're like looking at all these. Yeah, okay, good. Yeah, any? Feeling good? Yeah. Okay, so what I now want to show you, so here is this project right here. So this is the board support components for expressive development boards. So for all of the expressive development boards that Expressive makes, there are a bunch of different sensors and things and just peripherals that Expressive has used in their projects. And what Expressive has just done is they have organized all of the like code that they have gotten working for their like peripherals. So in this case, like on our Rust board, this repository will actually provide like a really nice interface to the temperature sensor for us, and we don't need to like worry about the actual like implementation details of it. So okay, yeah, and you're welcome to just kind of Google this and find this. It's a really great resource. So what I can now do is look up, I think it's components, and is that right? Yeah, and then here's the ICM42670. This is the whatever the IMU. Cool. And then inside of this now, we can see, I'll open up include. We can see that this library is provided to us. And look at this. Okay, does this look familiar at all? Like something that we just talked about? Yeah, so this is the different modes for the power management. Looks like there's other things too, like here it's setting like the sensor like speed at which like the data is actually sampled from the accelerometer sensors like into the accelerometer register, which then we can read out. Similar with the gyroscope. here we can turn on the gyroscope, put it in off mode or standby mode or low noise mode. And similar, I think, with the accelerometer somewhere. And then here is where we can now interface with it with using all these functions. So getting device, set power, gyroscope set power, and whatnot. And cool, okay. So I have cloned this repository in advance. So I cloned the repository in advance, so I'm going to quickly pull it up and we can walk through kind of just what the starter code is looking like. Okay. Okay, anyone else use this library? I saw a lot of people in lab yesterday were just using the, doing it all like from scratch by reading the data sheet. It does help a little bit, yeah, using this library that Expressive provided. But yeah, you're welcome to do it in any way that you find easiest. So, okay, here is the starter, well, I guess not quite the starter code. I modified this example for class today. But here we can see, so here is here's the same library that I just showed you. This is from the ESP like board components project. And we can see the implementation if we want of like all of these functions as well. We could see like how they get the device ID, and we can do that. Where is it? There we go. Here it is. So this is so right here, I guess this is the implementation for device ID. If you want, we can see how data is read out. Okay, so there we go. If you're interested in how data is being read out from this sensor, so it uses I2C master transmit receive and passes in the corresponding data that we need. You can see we have to pass in the like start address and then the data buffer that will be filled with data link. Okay, so if we want to just get something kind of basically working on this, then, okay, does anyone remember? So what was the very first thing that we need to do with the sensor? Yeah, just shout it out. Powered on, yeah, absolutely. Okay, so what we can do, oops, okay. So I guess maybe the first thing is, I guess we can quickly, yeah, good, okay. So actually, I'll give this to you right here. So the first thing that we need to do is actually go and create a like an instance of this ICM like struct that will handle everything for us. And yeah, I guess I'm calling it like I2C handle right here, and I'm passing in the address, which I believe is assigned in the SDK config. Okay. You can also find this example like on the repository. I'm modifying it slightly, but okay. And then here I will go and fill out all of the extra configurations. So there we go. So here I'm just setting kind of the, I don't know, just for fun, I'm setting these kind of frequencies for everything, for reading the like data per second and like the data register like frequency. I just found that these values worked. Okay, yeah, and then now in our app main, so I'm going to now bring in, so I will now create a dummy value for the accelerometer, dummy value for the gyroscope, and then a dummy value for the angle that we can track. And notice, so this IMC value T right here, if I open this up, this actually comes from like this example project where it's just a struct with X, Y, and Z. So there we go. So cool. So now we can go and run these init functions. So this is going to initialize the bus and initialize the sensor. And then now what I need to do is power on the the accelerometer or the gyroscope. In this case, I'll just go and turn on both of them. And the way I do that is with this Excel set power function, which I briefly scrolled past earlier. So you can see here's the Excel set power function. And so now this will set it to the low noise mode. And if we look at what is happening here, we can see that it's taking in the state value, and you can see it's ANDing it with OX3. So it's just grabbing the bottom kind of 3 bits here. Notice that's different from the gyroscope set power because it's grabbing the bottom 3 bits, but then it's shifting it by 2. Okay. Why are we shifting it by 2 in this case and not shifting it by 2 in this case? All right. Yeah.
Because accelerometers, it's 0 and 1, and gyroscope is
Exactly right. So the power management register that we saw, where's the data sheet? So the power management register, so the bottom 2 bits are reserved for the accelerometer, and then the next 2 higher bits are reserved for the gyroscope. That was just something that we saw in the documentation. Yeah, it looks like they are properly accounting for that in this in this implementation. Okay, then after we go and initialize them, now we can just immediately start reading out the data. So what I'll do is I'll make a while loop. And I can run the get data function. I'll quickly find where that is. So where is the get? So I don't think I need sensitivity. I could get raw value, but I think we can just go straight to the actual value, which is calculated for us. Yeah, so here is Excel get value. And you can see what it does is it divides it by the sensitivity value, which I did not show, but in the documentation, in order to get the correct angular velocity and whatnot of the accelerometer and gyroscope, we need to divide it by this internal kind of sensitivity value. And if we want, I guess we can find out where this is. So yeah, if we get sensitivity, what it's doing is it's checking the kind of just the configuration that we've set up. And depending on the configuration, just in certain modes and whatnot, there will be certain values that we just divide by. Yeah, cool, okay? So yeah, we can now get the value. Notice that it's getting everything. It's getting X, Y, and Z for us. So I can go and fetch this. Actually, just copy this in. Cool. Okay, and then now we could probably just start reading out what we grabbed. And then we can do a quick kind of sleep. And hopefully this works. Okay, let's see. Okay, hopefully this works. That's fine for now. Okay, so just by kind of looking at this, does this kind of make sense? So let me flatten out this this sensor. So does this look somewhat reasonable? I guess it's kind of hard to see. Let's actually just go and print out the accelerometer. Okay. Cool. Is something kind of strange, or is it all good? Makes sense. Is it reading the same? Is it reading the data in the same format as the iPad was? Something slightly different here. Yeah. Yeah.
Z is 1.
Z is 1. Why do we think it's 1? Yeah.
Is it measuring is it the multiplier of actual gravity?
Exactly. Yeah. So it's 1 times gravity. Yeah. So this is considered 1g. So if you wanted to convert it into meters per second, we could just multiply it by 9.8 or whatever. Yeah, exactly. Cool. With the gyroscope, we could imagine that would probably look like 0 until I wiggle it. So let me go and test that out. Is there a question?
Because it's divided by sensitivity.
Yes.
Sensitivity gravity.
Yes. No. Wait, sorry. sensitivity is just a multiplier that is explained in the documentation that does not have to do with gravity. It's just kind of like a, you can imagine that the larger the value that you have to divide by, the greater, like the worse precision you'll have, but the larger values you're allowed to read in. Kind of, it's like a trade-off thing. Yeah, but okay. And then cool, so here we can see, so I'm not currently touching the gyroscope at all, but now if I go and start wiggling it, then now we see a bunch of data. Okay, so it looks like it's pretty good, but if I leave it on the table again, it's like it's mostly 0. Okay. Any guesses for what the unit of this is? So here, I'm gonna show you what I'm doing. So I'm just doing get Excel data, and then I am just printing it directly out. And each of these values, they are floats. Okay. Yeah, any guess for what this unit is? Yeah?
Degrees per second?
Yeah, so I think these are probably degrees per second. It looks like if I flip it around, it might be, that's probably right, yeah. It's definitely not radians. If anything, it might be 2 times degrees per second, but I don't know, yeah. Probably good enough for this lab, yeah. Cool. Yeah, question?
I think it labels gyro degrees per second right there in the
This degree per second? Yeah.
I guess that's degrees per second.
Yes, yeah. I did write this out. Degrees per second. Yeah. Okay. Also notice here that actually, yeah, I also wrote out G for number of G's for the accelerometer data. Yeah. Cool. So I know what you're thinking, right? You're thinking okay, so the accelerometer's cool, gyroscope's cool. Wouldn't it be nice if we could somehow kind of just combine them together and get something just a little bit more precise? Because actually, that's what real kind of designs out in the world that are successful will do. Is they'll have probably an accelerometer and a gyroscope that work together, but maybe they'll also have a compass, also known as a magnometer, which measures the Earth's poles. Maybe you have radar as well to test how far away you are from the Earth. You could also have a map of the gravity in an area. If you're going to be flying a really far distance and you're using the accelerometer data at all, you want to make sure that when you fly over an ocean, that now you realize that your gravity, your acceleration is going to drop a lot because now there's less rock below you versus other places that maybe there's more gravity. You now need to adjust for that. Or yeah, potentially you could have weird sonar things, kind of just the more data that you get, the better. Okay, now there are lots of different algorithms to combine the incoming data and kind of make decisions on that of what your position is, and that is generally called a filter or a tracking filter. Because what we actually want to get, the sensor data is cool, but actually what we want to know is not just these random sensors raw values, but instead we want to know the actual position and angle of our device. And if I actually pull up my iPad again, we can see that my iPad actually has these registers that my device is just able to read at any time. You can see here I have linear acceleration. Oh, sorry. So here's my iPad again. And here you can see I have linear acceleration as data that my iPad is offering up to its from its operating system to this application. The application is just reading out. It's running the get linear acceleration data, and it doesn't have to worry about actually reading the internal sensors. Or similar, I can I can grab the rotation vector, or I can grab the gravity. And what it's doing is it's doing all this kind of complicated mathematics to calculate this, because this is the actual data that we care about. We don't actually really care about specifically what the accelerometer is reading, because this is just a small data point. And what we can do in this project right here is, so here we see this extra struct right here, complementary angle. And if I look this up, we can see actually that we have this complementary filter right here. Okay. So is this complementary because it's like, oh, this is just like it's like complimentary like breakfast or something, or it's or like what does complimentary here mean? Why is this complementary? Yeah. Well, because it's adding things together. Like it's adding both the data from the accelerometer and it's adding in the data from the gyroscope. And then from that, it's now producing this data right here, which is actually the thing that we care about, which is roll and pitch. And yeah, there's extremely like, you could honestly do like an entire like PhD dissertation on like all the different types of tracking filters and things. There's all sorts of different algorithms out there. This particular algorithm, I think it's like really simple, the one that they provide us. I think it literally just kind of adds them together. We can kind of just see. I guess it does like arctans and, oh, I guess it does. Okay, it does like kind of complicated stuff. But yeah, so there's different sort of algorithms that combines the data. And so what we can do now is instead of just printing out this kind of like confusing, accelerometer, like raw data, now we can go and print out the this like angle value, which so I'm initializing right up here, and then I can go and calculate this by running this filter function. So I can run the filter, and now this will give us like the actual angle of this with a little bit more precision. And cool. So now in theory we can run this. Okay, cool. So if I hold it like pretty kind of still, we can see it's like saying roll is like basically 0. But now if I like roll it forward, we can see now it goes higher. Okay, and if I roll it back, you can see, I guess before it was lower. Now it's going higher. Same with like pitch. So pitch is like side to side. And because we are combining both the accelerometer data and the gyroscope data, now this will give us more accuracy. Okay. Is there anything missing though from this? Okay, like I don't know. Do we have any like any pilots out here or something? Like something's missing here. So we have roll and we have pitch. Yeah, what's the final thing? Yaw. Yeah. Anyone heard of yaw? So so roll generally is like this, and then pitch is like up and down like this, but then yaw is usually side to side. So we're actually missing yaw from this. And we probably could calculate yaw with like a pretty high degree of confidence, but generally if we want to actually calculate yaw with like, in the official way that actual planes will calculate yaw, they will instead, actually does anyone know what they will use to calculate yaw? Or to at least help calculate yaw. Okay, wait, question. So let's say I wanted to just like, maybe we got any hikers out here. So let's say you wanted to hold like a device and you wanted to see like in what direction you were standing in. Like you wanted to see like, am I like facing north right now or am I facing like west? Like what is that device? Yeah, it's a compass, right? So what a compass is, it's a magnometer. So you're measuring the magnetic fields, the magnetic poles of the Earth. And so what oftentimes, like what other sensors will have is, they won't just have accelerometer and gyroscope. They'll also have a magnometer, which will now help measure yaw. And that'll be now another extra bit of data that they can throw on. And honestly, they could have probably just calculated a yaw and it would have been good enough. But I think that they were cautious about putting on a like yaw value here for people to use, because this sensor is not really meant for calculating yaw. Instead, it's just meant for calculating roll and pitch. Okay. Is there a question? Okay.
My question was, do you have to like implement?
No, you can, honestly, you can probably just get away with, with either a pitch or roll or, But you can get like really deep on this stuff. Honestly, I would also recommend like watching like more videos on it. Like there's really great like visuals out there that if I had more time, I would make like this really great elaborate like lecture, but instead I feel like I'm kind of just showing you how to get this code working, and then you can experiment it on your own. I will publish a few like really good resources that I like, filtering and tracking is such an important thing to understand these days, especially for like self-driving cars. If you want to track now like an object moving across like a screen, you want to now, yeah, it's like kind of interesting. Like you imagine, like as humans, we're really, really good at tracking things. We're really good at like as we're being fed in like a series of images into our eyeballs, we're really good at realizing that if something like moves, we're good at realizing that that's actually the same object and it has just moved. But for computers, it's actually a fairly complicated thing. It's like, well, what is an object? Are there those multiple objects, or is that actually just one object? And also, like, yeah, as it moves, like, oh, did that just like become destroyed and then like become a new object, like somewhere completely differently? So yeah, filters and tracking is like an extremely complicated field. Okay, so that's probably a good enough kind of overview that I wanted to talk about today. Yeah, any questions on this? Is anyone now going to go and rewrite any of their code for Lab 4 to make it a little more accurate? Yeah, cool. Okay. Any final questions? I'll post the, I won't post this exact code because it kind of gives away too much. I will post the lecture though, so you could copy it down. But I will post the link to this repository, which gives you like most of what I just did. Yeah. You all also can take a picture if you want. Yeah, question.
Wait, but also, I guess,
Yeah.
even if you don't use, I guess, like, the role and different, if you just use accelerometer, but then it still works, like, that's okay, right?
That's probably fine, yeah. I would recommend maybe using the official library, just to gain practice with that. But if it works, that's fine, because we also want you to learn about Bluetooth in this lab, and that's a lot of kind of learning outcomes, so yeah. As long as it works, that's probably good enough for a checkoff. Okay. Anything else? Final? Okay. Well, I will see you on Monday. Please, yeah, start this lab as soon as possible if you haven't already. A lot of people have run into a lot of issues, so good luck. Yeah, cool.